by Huanhuan Li, and it will be on the injective Leavitt complex.
Okay. First, I want to thank the content for giving me this opportunity to give this talk. Here I'm talking about the injective Leavitt. This is part of my PhD work. So first, let's have a quick background and let's see our question. About 10 years ago, Professor Cross, he introduced the stable derived category of finite dimensional algebra A. Here, this category, in fact, it is a home topic category. It consists of complexes. So first of all, complex, it means here for complexes or models, it is a sequence like this. It contains all these xn plus 1 are objects or models. And here we have the difference of dn, which are morphisms of A models. And it is satisfied that here we have given minus 1x. It satisfies that the comparison is there. We call this sequence a complex. So this category, it contains a cyclic complexes of injective A models. So that means each component here is an injective A model. And it's a cyclic. We will give the detail for a cyclic complex. So this category here is a triangulated category. That means triangulated category, that means it is an additive category. It has a shift factor and it has distinguished triangles. He proved that this triangulated category is compactly generated. That means that it exists special objects in this category, such that this category is the smallest triangulated category, which contains large span objects and is closed and after coproducts. So here coproduct is the product of the complexes. So we know that at this moment we have the injective, the level path algebras of graphs. So it was introduced by Professors Ibrahim Aram, Ram, and Untitled. Professor Chen and Yang, they have a result like this. They just consider finite directed graph E without things. They have this triangulated equivalence. First, let's see this category. It is the stable derived category induced by Professor Cross. So here, let's see this algebra. This is a cosine algebra of the path algebra, KE. So here I use KE cosine G square. See here, this square, I mean, it is the idea generated by the paths of length 2, all the paths of length 2. So here, the idea is generated by paths of length 2 in the graph. So this cosine algebra, in fact, it is a finite dimensional algebra. It is, as a vector space, it is the double sum of K1 and K0 and K1. Okay, so now we know the left side consists of a cyclic complexes of injective models. And it's a triangulated category. The right side, this category is a differential graded category of the Leavitt path algebra. Here, this Leavitt path algebra, we know that it's naturally Z-graded. Here we can say as a differential graded algebra with trivial differential. That means the differential is 0. They give this triangulated equivalence and have these functions. But we don't know. We also know the inverse functor. However, give us an object in the right hand. We don't know what's this on the left hand. We cannot write it down. So here we have question. The first question is I just want to consider this special object, the level plus algebra. I want to know its pre-image. If we find its pre-image, because here in the derived category, this algebra is a compact generator. So the pre-image must be a compact generator of this category. And the second question is that what is the connection between this pre-image and the level plus algebra? Because we know that they have this kind of relation, so we kind of think that this pre-image should carry some information of the level plus algebra.
The top arrow, is that an isomorphism?
Sorry?
Yeah, that one.
This one?
That's an isomorphism? That map, it is.
The map is, sorry.
Yeah. The map
is
is character.
The map is characterized by these loops, or we can see it's a localization of the homotopy category.
So you might say it's a homotopy equivalence.
Yeah.
That's equivalent of categories.
Yes.
Triangulate.
Okay, so we have that we have the result that we know the basis of the level plus algebra. In fact, sorry. All these people they give the basis for the level plus algebra. Professor Hammond and Dr. Presser they give a basis for the weighted level plus algebra, which is a generalization for level plus algebra. So here we use this basis of the level plus algebra. We construct a complex. We call it the injective level complex. And then we prove that it's a compact generator for this category. And continue, we can find that the relation between them. We find that the differential gradient and morphism algebra of the injective level complex I is quasi-isomorphic to level plus algebra. So here, quasi-isomorphic. So first, as algebra, they are not isomorphism. But taking cohomological groups, they are isomorphism. So that means we're taking this, they are isomorphism. So that means quasi-isomorphism.
May I ask a question? What is a Leavitt complex?
We will conduct it later.
Okay.
Yeah. So here, we will know what is the category, what is this category. And the second part, we will construct the injective level complex I. Then we will prove the connection between the endomorphism of the injective level complex and the level plus algebra. So let's first we recall what the complex is over an additive category A. A complex is a sequence like this. As I said, as we recall here, this is objects in this category A, and here are all morphisms in A, and satisfies this relation. And we call this xi the ith component of this complex. So given us two complex x and y, we have a chain map F. A chain map, it is morphisms. It is a sequence of morphisms Fn. Fn is from xn to yn. It's a morphism in the category A. And it satisfies that this square, each square is commutative. That means if we go this map and this map, it coincides with this one. So this kind of Fn is a chain map. So now we have a category of complexes over this category A. So objects are complexes of A, and the morphisms are these chain maps. Then now we can introduce the homotopy category Ka. So here, this A is still the additive category. So now we need to introduce the concept of a no homotopy chain map. So suppose F is a 10 map. It is called no homotopy if there exists these maps in A such that this satisfies. So that means what is I will do a diagram here. So suppose we have 10 map from X to Y. So X is this. So we know here we have differential. For Y, we have similar. We have yi plus 1, and we have the differential. Here I minus 1y. So here there exists Sn. That Sn is from Xn to Yn minus 1. So here I use I. So here Si. So here we have the map of Fi plus 1, and here Fi minus 1. So we have many these Si maps. So that means this is we go this map and this we put them together. This gives us this Fi. So if this holds, we will call this T map as a no homotopy. We denote by this. Given us two maps F and G, which are both from X to Y, we call their homotopy if the difference is no homotopy. So now we can have this. We have this no homotopy 10 maps from X to Y. So it contains the 10 maps from X to Y such that it is no homotopy. So now we have the category, the homotopy category over this additive category A. So objects are still complexes over A. Morphisms, here morphisms is the quotient. So here are 10 maps. We quotient this. So that what this means? That means if we have two 10 maps with a homotopy, then in this homotopy category, there are some morphisms. So now let's give definition for a cyclic complexes. So for cyclic complex, we call the kernel of dnx the nth cocycle over x, and we call the image of dn minus 1 the nth co-boundary of this complex. We call this quotient the nth co-homological group of x. If for one complex x, all this co-homological group is 0, then we call it a cyclic. So that means for this complex, the kernel for each of this map is exactly the image of the previous map. So here, in our case, we will consider K is any field, and we consider just the finite graph without sinks. We consider this algebra, the quotient algebra or path algebra. All the paths of length 2 is are 0. So it's called radical square 0. That's because the jumping radical, the square of the jumping radical is 0. So we denote D is the standard key duality. And we denote II, it is D, EIA. So here in EI, I use EI to stand for the trivial path corresponding to the vertex I. And here, so we know that EIA is a projective right in model. So here we use the duality. We got II is an injective left in model. So here for the injective model II, we have a basis. In fact, it's the dual basis of this projective model EIA. So here I use EI has and R has to denote the dual basis, because for usually we use star, but because in level path algebra we use star for the ghost edges. So here I change another symbol, use has. So for this algebra A, we use A injective to denote the category of injective A models. We use Ka injective to denote the homotopy category of complex of injective models. So here we recall for any additive category A, we define the homotopy category Ka. And this category, it is a subcategory of Ka injective. It consists of those objects which in this category, which is a cyclic. So this category, it consists all these cyclic complexes of injective in models. So this is exactly the stable derived category used by Professor Cross in this paper. Okay, so now we know what this category is. In fact, it carries very good structure. It is a triangulated category. So here we didn't give the details for this, but we know that it's a triangulated category. And in fact, later in this paper, he saw that this is a compact generated triangulated category. So that because of his result, I can try to find a compact generator. If it's not a compact generator, I cannot find one. So let's do the second part. We first recall the basis of the level path algebra. So here, for each vertex V in our graph, we know that our graph does not have sinks. So for any vertex, there are edges going out. So we just fix one, which is starting from the vertex V. So we fix, we call the fixed arrow the spatial arrow starting at V. Then after we fix the spatial arrows, we can have a K basis for the level path algebra. It consists of all these elements in this form. This is zero path, this is the path and the ghost ones, and this is the ones in this form. So here I write the comparison from right to left. Yeah. So here. This P and Q, they satisfy that the range are the same. And if we write P and Q as sequences of edges, then the last edges either are different or they are the same, but it's not special. So remember here we fixed the special one. So let's see an example for to see what kind of elements, to have a feeling of what kind of elements are basis elements in the level path algebra. So from here, we just have one vertex and two loops. We chose one. We chose alpha 1 is special. So here, by this lemma, we know that we have basis. So I just want to do, So here, because this is our CK2 relation, I should first see that. So for this graph, we know that E1 is a basis element. This is our lemma is the first. E1 is the basis element, and we know that alpha 2, this is a basis element because this is Q, this is P. They are both alpha 2, but they are not special. But by this CK2 relation, we know that alpha 1 is E1 minus. So it's already represented by it is already a linear form of this basis elements. So this kind of elements is not basis elements. So I just try to let us have a feeling about why we do not use this kind of why this elements is not basis elements. So here what I want to do, I just pick those kinds of pairs, PQ, such as the P star Q are basis elements. So I call these kinds of pairs admissible pairs. So this is exactly, we just pick the pairs in the graph E. So I try to use this pair to construct the injective level complex I. So here give some notation. For its vertex I and an integer L, we set BLI, it's this set. It consists of a admissible pair PQ such that the length of Q minus the length of P is L. And the starting point of Q is I. So here, for a set X and an inverse M, the coproduct Mx, it is the copies of M. So that each direct summand is a copy of M. Here we use zeta X, this index, to indicate that this direct summand is corresponding to this element X. And for elements in M, we write M zeta X. We use this to indicate that this element is belonging to this direct summand. And here we need transactions for pass. So given a pass, we have two transactions. Either we cast the first edge or the last edge. So here we can see the non-trivial pass. So we have two kinds of transactions. And here for a special arrow alpha, we set S alpha. It consists of all these arrows with starting from S alpha, but it is different from alpha. So now we can give the definition for this complex, for this injective level complex. So here we only consider final graph without things. So the complex, to give the complex, we need to give each component. So first we give the S component. The component is the sum, the direct sum of these injective models. So here I will remember that it's the injective models corresponding to the vertex I. And BLI is the set consists of these admissible pairs. So here, because our algebra A, so remember this is our algebra A, it's a finite dimensional algebra. So here the direct summand is still injected in model. Because finite dimensional algebra is it is not algebra. So even BLI is an infinite set. The direct summand is still injected in models. So here we need to give the differential map has L from IL to IL plus 1. So remember that we have basis for this injective model. So we just and here is a direct summand. So we just pick any object, any pair PQ in this BLI. So we have to pick any PQ in this BLI. We have a direct summand I zeta. We use zeta PQ. We know that I has this basis, so we just need to define the map pass L on these basis elements. We just need to define the pass L on the basis elements. This and this. This is the basis elements. So this case is mapped to 0, and this case we have two cases.
I have a question. In the admissible pair, do you fix the L, the length? Is that what L is? How is the L?
L should be
admissible pair?
so for the here for any integer, we first give the component. So we got L, and we also need to give the differential for any integer L.
But my question is, I forgot the definition of the admissible pair. When you're picking the P and Q, do you restrict the length of the paths?
Here if I choose PQ in here, the length of Q minus the length of P should be L.
Oh, okay.
Yeah. Here this is the length. The length is the difference of these two paths.
And can they be concatenated? You start with the vertex I from Q, and then you concatenate to. So do they resemble like the?
So this one is corresponding to Q P star in the level of path algebra. So this is exactly the length is the degree of this element. So because I write the comparison from right to left.
Yeah, that's fine.
Yeah. Okay, so we give this map, and what we need to check this differential is in morphism. Oh, we will not do the detail here. And we need to check the partial, the comparison for partial and zero. Yeah, this is quick can be by the definition of partial L. Yeah, because this kind of element is mapped to zero. So, and the image for this kind of elements are in this form. So we use partial L plus 1 and all are mapped to 0. Let's see an example. So what is the injective level complex for this graph? So here we need first to write down the set BL. For any integer L, we need to write BLI. I is the vertex. Here we only have one vertex. So BL1. So we just denote that as BL. So it consists of those admissible pair, PQ, admissible pair, such that the length of Q minus the length of P is L. And the source of Q, of course, is 1 because we only have one vertex. So here for BL, we can write down what is BL. When L is greater than 0, then we will find that BL just consists. So here we can first see that the length of Q minus the length of P should be L. L is positive, so the length of P must be greater than or equal to L. So if the length for this Q, if this is of length L, then it is the power of alpha, X power of this. So here only U1, there's no choice. If we use Q as L plus 1, then here the length must be of 1 because the difference of this length should be L. But now if I put alpha here, then it is not a admissible pair because we only have one loop. It must be special. So this kind of thing cannot be hidden. So we only have one object here. And when L is 0, we have BL. B0 in fact it just contains U1, U1. When L is negative, we have BL. It just contains alpha minus L and U1. So we only have one element for each set. So now our I1 is the only injective model because we have one vertex I. So we denote it by I. In fact, it's DU1A. Here, U1 is identity, so it's DA. Because our A is random square Lie algebra, it only has two bases in A. R is U1 and alpha. So here, BA has two basis elements, U1 has and alpha has. So now we can write this injective level complex. In fact, here because our BL just consists one element, so we have I. For each component, we just have one copy of I. So this is L complex component, and we also need to give the definition for this partial L. So for partial L, we pick. We know that the basis is this, so we pick E1 has, which is in. Remember, we use this zeta. When this is L, this is. Here we need to consider L is greater than, or L is 0, or L is smaller than this. So we will consider case by case. If L is positive, then we pick an element here is in this form. E1 has E1 alpha L. So by the definition, it goes to 0. And for another basis element, alpha has zeta E1 alpha L. The definition, we will use the definition here for this one. Let's see, it's not this case. This case, the one, in this case, Q should be a true path, but here L is positive, so it's just in this case. So it's mapped to U1 path, zeta U1 alpha L plus 1. So we know how it maps for this case. So similar for these two cases, we can test that. So in fact, we can simply just write, we do not use these signals here because we just have one direct summand. So just map this to 0 and this piece element to this kind of one. From this point, for this example, we can see it's a static complex. The kernel is generated by this element. The image is similar. The image for this is also this. So it's a static complex. Okay, here is another example. Here we choose alpha 1 is special. So we take U1 to be E and we need to describe the admissible pair in this set. In fact, a pair PQ or path length in this set, if and only if the difference is of this length is L, and they do not end with alpha 1 simultaneously. From this description, we know that PL is an infinite set. In fact, the injective level complex looks like this. So here for the partial, we just give one element for an example. As an example. So here, by the definition of the partial, it is mapped to this, and then need to do something. Because here we have two loops. Alpha 1 special, we still have alpha 2. So here we have minus. From this complex, we cannot directly see it's a static, but we can prove generally that if E is finite graph without things, then the complex is a static. We just use some linear facts. So now we know that we construct this I, it is a cyclic, and each component is injective in models. So it's in this homotopy category. Then the next part we need to prove it is a compact generator in this category, in this triangulated category. So here we recall some notations of triangulated categories. So we suppose T is a triangulated category with arbitrary coproducts, and take an element L. It is called compact if this functor commutes with arbitrary coproduct. Then we call T is compact generator if there exists a set S which consists of compact objects such that for any non-zero element T, this home is non-zero. So here, this has a shift. This is the shift functor for this triangulated category. If this set S here, this set S consists of a single object S, we call this single object a compact generator T. In fact, Niemann he gave an equivalent description for this compactly generated triangulated category. This is equivalent to say that this T is the smallest triangulated category which contains this object and closed and this arbitrary coproduct. So it has this small property. So what we got is that for our case, we can prove that this complex is a compact generator. In fact, we just give us the guess for the proof. So here we need a notation. So remember we defined this BLI. So now we give a partition for this BLI. The partition is given by if the length of Q is n, then we can have this. This is a subset of BLI. So this gives us a partition for this BLI. Then we can have a subcomplex of this I is given by this. So now we can have a exact sequence of complexes, which splits in each component. So that means it's split. So that means for each component, each component of I is a direct amount of the component of M and C here. Yes, so here, because M is a subcomplex of I, so we have this inclusion. So here we have the coconut complex. So we call it coconut complex of I, because later we will use this coconut complex to prove that I is a compact generator. So here we have a picture for this complex I. So the whole piece is our complex I. So the component of I is the direct sum of the objects in this column. So this is the minus 1 column, minus 1 component. This is the zeroth component. And here, the blue diagonal line is the subcomplex L. So the part of this line, the other part is the coconut complex C. So we can easily to prove this. This is the coconut complex is a union of a limit of these subcomplexes. So in fact, we can see the subcomplexes from here. So remember here, we just see the black lines. So the first black diagonal line is the first subcomplex C1. Then the second two, these two diagonal lines give us the second subcomplex. So we can continue on. We can get subcomplexes of the coconut complex. So using this and consider this triangle, we can prove that it's a compact generator. So the next part we will show the relation. So here, this morning Professor Harrod already introduced the graded models. So here we need to consider the differential graded case. So first we recall what's a differential graded algebra. So it is first a graded algebra, but we need to endow it with a differential. So it has a differential of degree 1, satisfies this rule. So we can think it as a complex. So that means for differential graded algebra, we didn't know about it like this. It has a differential. We know that it's graded, so we can treat it like this: an plus 1, and so on. This n minus 1. And because it has a differential over degree 1, so we have this. So we can consider it as a complex such that its differential is compatible with the multiplication. So for a DG algebra, we can have a DG model. So that means we have a graded model first. And also this model has a differential over degree 1. Also the differential is compatible with the model action. Compatible with the model action. So here we have this thing. That's because we changed the positions for the element A and the differential here, because we have degrees, so that we have this sign here. So similarly, we have the right DG model. So then we need to give the definition for DG and morphism algebra. So then for two DG models, we can have a Z-graded vector space here. such that each component here, it consists of the maps of degree n, and it also satisfies this. In fact, this is said that it is similar as to say that f is a map, but here we have degree, so it's similar to a and f change their position. So here we have these degrees here, and we can endow this graded vector space differential D. The differential is given by the differential of m and n, because our DG model have differentials. So we use this can have a differential for this whole space. So if m and n are the same, then we have a DG algebra here. We can check that here. It's a DG algebra because we now m and n are the same. We have the comparison as the multiplication. So here we also similar. We have the DG operator algebra. Usually we have operator algebra, but here for DG case, here AB is not BA, but we have this because we just changed the position here. So here, let's recall what is the DG bimodal. Yeah, for bimodal is we can guess that it's first should be less the DGA model and also should be a right DG B model, such that the action is compatible, such that these two actions are compatible. So for this bimodal, we have a definition for right quotient balanced. So that is to say that giving us a DG bimodal M, we can immediately have a DG homomorphism from B to the endomorphism. This is the DG algebra of M. So here the action is defined by the right B action of this model M. So that means here, suppose M is a DG bimodal. So we can have a map from the DG algebra B to the endomorphism algebra of M. So here we use the opposite ones. So for any element B, we have RB. It's a map from M to M. So for any element M, we use R. The definition for RBM is induced by the right B action. So that means we use B to action on M. But here we change the position. So here we have this. The degrees for these two elements to multiply. So if a bimodal M, it is satisfied that this homomorphism is quasi-isomorphism, then we call it is quasi-balanced. So that means this is we taking the cohomological groups. We have the indices isomorphism. Inspired by that, we have that definition, and then we observe that we have this result. For this quasi-balanced model, we can have a triangle equivalence from here to here. So for our case, suppose we have this I, it is DG balanced, then we can have this isomorphism, and so we can get this triangle equivalence. So inspired by this result, we want to make this injective level complex to be a quasi-balanced bimodal, to be a DG balanced DG bimodal, which is quasi-balanced. So but now this I, we remember that it is a complex of A models. In fact, we can consider it as a DGA model. As a DGA model, because here we consider this algebra A is constituted in degree 0. Then now, this complex can be considered as a model, as a DG model, because we put the components together. Then we can check that it is a DG, a left DGA model. So what we need to do, we need to give it a right level path algebra model. So here we need to define a right model here. And then here just the formulas. And then we need to prove that this is, we consider this is DG algebra and the level path algebra as the DG algebra with trivial differential. Then we can prove that this right action in the previous page makes it a bimodal. So the rest of the work is we need to prove it's cross-balanced ones. So that one we can use. So that means we need to prove this is isomorphism. So for the injective we use for the injective we use this graded unit theorem. So we can check that. For surjective we can take any element we can find the pre-mid. So that's it. So now we can have our second result here. From this result, we can deduce that the DG endomorphism algebra of the injective level complex is quasi-isomorphic to the level path algebra. So now we answer other question. So now we have the triangle equivalence. So remember, before we have this, we have here, we now prove that I is quasi-balanced. Then we have this as a map. In fact, we can show that this functor it sends I to the level path algebra. So that means the pre-mid of the level path algebra is the injective level complex I. That's all for my talk. Thanks very much.